Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
We know that algorithms are amazing human achievements, but they're not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we hope you teach mathing, building relationships with your students and grappling with mathematical relationships.
And we invite you to join us to make math more figure-outable.
Hey, happy birthday! Well, not really your birthday, but we are recording a little bit early. I know I'd throw you off. We're recording just a little bit early, but when the day the episode comes out, it will be your birthday.
Wow, look at that. The whole world celebrates my birthday. How
know.
fun is that? Yeah, there's always a party.
It is. Okay, so listen, we've been hearing, I say that, I know I've been hearing, I know you probably have too, about people loving the higher math that's been happening.
Yeah, interesting,
I know.
Right?
It's super fun. And I've been hearing from some elementary teachers who have been really excited about trying out some middle school and high school content. And it's been kind of fun, right?
Yeah, actually, when I was on my trip to Europe, it was fascinating to hear from the number of people who said, we really like listening to the podcast, even when it's not the content we teach, because we're able to mess around, play with, think about that mathematics and realize math is figure-outable, like stuff that we don't even deal with a lot and maybe never got when we were taking it. It's kind of fun to figure it out.
Back in November, we got a review from Natalie E. from New Jersey, and she said, I started listening to the podcast while researching ways to support students struggling with dyscalculia. And as I listened to more episodes, I found myself diving deeper into the world of numeracy. Goodness, Kim. Unlike other podcasts that often seem to focus on selling products rather than providing valuable content, the episodes are full of practical insights. Pam and Kim guide listeners through mathematical concepts slowly and deliberately, helping me reason through problems and make connections in ways I never thought possible, especially in more advanced math. Thanks to this podcast, I've made incredible progress in my numeracy journey, and now I feel confident helping my middle school son tackle algebra. Thank you for everything you do.
Wow.
Isn't that fun? Yeah.
Oh, Natalie E., thank you.
We should talk.
Amazing.
I've got a middle schooler taking algebra.
So, and I'm noticing that the title of this review is life-changing.
Yeah.
That's super cool. Thanks.
All right. So how about we do a little bit more math today?
Let's do. When I was in Bulgaria, I was tasked kind of last minute, just a little bit, with doing a problem string with a group of year 10 students. So they talk about years and not grades. So kind of a little quickly, I came up with one of the problem strings I've done before. I didn't write it, I grabbed a string that I'd done before. That we actually have on the website. So maybe after listening to the podcast, if you want to see the modeling, you could actually go check out the problem string at mathisfigureoutable.com/PS. Don't do it now, do it with us here. But you could actually see it with a group of grade 9 students, so 9th grade students doing it. This is a group of grade 10 students. And let's have a little bit of fun. You ready?
Yeah.
Okay. So Kim, pick something that grows on trees that you would want to harvest off those trees to eat.
How about oranges?
Could be oranges, right? Could be, pick something else. Apples, cherries.
Ooh, cherries are yum.
In our area, there's a lot of pecans. Do you say pecans or pecans?
Ugh, pecans.
Okay, yeah. There's people here. It's pecans.
Pecans, yeah.
Yeah.
I think it depends on where you are in the States.
Yeah, I think so too. So lots of, we could picture an orchard full of trees, and you said oranges, so we're gonna do oranges today.
Okay.
We've got this orchard full of orange trees, lots of oranges. And for this particular orchard, we know that it takes 20 workers 6 hours to clear the orchard. So if we say mark it, set, go, and the 20 workers that we have go out into the orchard, 6 hours later, we'll have the orchard cleared. All the fruit will be picked, and we're happy in the 6 hours, and the 20 workers can go home.
That's a big orchard, yeah.
Okay, there you go.
Big.
Well,
20 workers for 6 hours?
Yeah.
Yeah.
Okay. I don't know how many oranges they're picking, but there you go. Okay. So if that's true, that 20 workers working at the same rate each work for 6 hours and they can get the job done. The whole thing is done in 6 hours. What if tomorrow we're ready to clear the orchard, but only 10 workers show up? Oops, only 10 workers show up. What are we going to need to plan for?
Mad workers.
Okay.
They're working longer.
Yep. And how long will it take to clear the orchard?
It's going to take them 12 hours.
12 hours. Because, wait, 12 hours? Hang on. We halved the number of workers. So normally wouldn't we half the number of hours?
No, half the number of workers means that you need to work twice as long to do the work.
So it's almost too bad that you said that so fast, because every time I've done this problem string, whether I've done a lot of ratio table work or not with students, almost to a T, students will say, well, if you half the number of workers, then you half the number of hours. And so they say 3, including a very quick group of 10th graders that I worked with in Bulgaria.
Do you think it's because they saw you write it? Like, I don't have anything written down, so I'm listening to your story in the context.
Yeah, I don't know, but I'll tell you, for the rest of the string, you are going to probably want to write down a table that has workers on one side, hours on the other.
Okay.
Maybe. I know I did this with a group of teachers quite a few years ago. And the group of teachers, I asked the question and didn't take any answers and walked around. It was super interesting. There was one teacher who said what you said: if you half the number of workers, then you double the time. It will take you longer because you have half the number of workers. And this particular teacher was a special education teacher, and the teacher sitting next to him laughed and said, no. If you half 20, then you half 6. The answer's 3. And I said, well, say more about that. Like, why would you, if you half the number of workers, why does it half the time? And she laughed and said, because. And I said, why do you think it's twice the time? And the kind of quieter teacher said, well, because you have half the number, and then interrupted. It was a very uncomfortable situation. The gal interrupted him again and said, no. Just it's fine. It's 3. In that moment, I'm not sure I chose the right route to go. I kind of let it go, and I was hoping they would continue to talk about it, but I was smiling a little bit inside because I knew pretty quickly we were going to substantiate his answer and that we were going to let her go, oh, like maybe instead of just starting to do stuff, it's worth thinking about what's happening. So if you half the number of workers, it's going to take more time. In fact, it's going to take double the time. Okay. So far on my paper, I've got 20 workers to 6 hours. And then on that same table underneath that, I've got 10 workers to 12 hours. Cool. What if we had 40 workers show up? Double the number of workers from the 20 show up. What if we have 40 workers show up? How long will it take to clear the...
Well, you just told me it's double number of workers. So
sorry.
It's going to be half the number of time.
Well, it's not double from the 10. It was double from the original.
Well, you said double from the 20. So double from the 20. When I had 20 workers, it took 6 hours.
Okay.
So if I have twice as many workers, then I need half as much time as it took the 20 workers. So instead of 6, it's going to be 3.
And could you go from the 10 workers and 12 hours?
Yeah. So when it was 10 workers, it was 12. So 4 times as many workers, they're going to need a fourth of the time.
And a fourth of 12 is that same 3 that you just got. Cool. So 40 workers will take 3 hours. Nice. What if I find out that a frost is coming? Oh no, I don't even know if it freezes where you grow oranges, but whatever. I find out there's some catastrophe about to happen to the orchard, and we've got to clear it, and we have exactly 24 hours to clear it. So I'm putting now 24 in the hours part of my table, and I know I've got 24 hours to clear the orchard. How many workers do I need to hire?
If they're going to work continuously in that 24 hours, then you need 5 workers.
How do you know?
Because when you had 10 workers, that was 12 hours.
Okay.
And now you have twice as much time, and you can do it with half as many workers.
Oh, nice. Nice. I like that. Can you go from any of the other ones?
Yeah, you can do when you had the 20 workers for 6 hours. You have 4 times as much time. So you can take a fourth of the number of workers. So from 20 to 5.
A fourth of the workers can accomplish the same task in 4 times the amount of time.
You can go from 40 to 3 if you want.
I liked it when you said that you're going from the time. If you have a fourth of the time,
Mm-hmm.
then you're did I
Four
say
times
that
as
right?
much. 4 times as much time than you need
Yeah,
a fourth
thank
of the
you. Yeah,
workers.
4 times this time you can have a fourth the number of workers. Yeah, that's
Mm-hmm.
nice. Cool.
Mm-hmm.
What if 15 workers show up? And
Okay.
maybe people think about this before you just hear Kim just like go. But
Mm-hmm.
yeah, go ahead. All right, 15. You got something?
Yeah, I actually looked at the 10 first.
Okay.
I mean, yeah, I looked at the 10 first, and I wanted I guess I'll go to the 5. I don't know why the 10. I don't know why the 10 why I wanted to do the 10 first.
We can talk about the 10 in a minute. Go ahead and do the 5 if you want to.
Okay, so if I have 5
Workers.
workers, yeah, I have 3 times as many workers.
Okay.
So I only need a third of the time, which is 8 hours.
8 hours. So
Mhm.
5 workers were 24 hours.
Mhm.
So 15 workers, 3 times as many workers is only going to take a third the amount of time.
Mhm.
Yeah, thanks. I just had to say that loud to make sure
Mhm.
I'm actually writing that down. I'm like, so times 3 divided by 3
Mhm.
when I go. Yeah. So I'm that scaling often on a ratio table. We'll write, if I double the amount of packs, then I double the amount of sticks in a pack of gum. And in this case, if we are multiplying by 3 the number of workers, then we're dividing by 3 the amount of time.
Yeah.
Yeah.
And I think that's what I was thinking about when I wanted to go to the 10
Yeah.
was the 10 was 2/3 of the time that I had. I had less time. I only had 2/3. Or sorry, the workers. I only had 10 workers. So I had 2/3 of the number of workers.
Okay.
So they're going to be able to do it faster. Um, and so I needed the 12 to be 3 halves. You said 15 first, right? I can't remember.
Yes.
Okay.
Yes.
So,
I gave you the
so,
15.
so I
Yeah.
had three halves as many workers. So they could do it as 2/3 as much time.
And if you don't mind, I'm going to repeat those numbers. So from
Yeah.
10 to 15, you're
Hmm.
saying multiplicatively to get from 10 to 15, that's
Hmm.
10 times 3 halves is 15.
Hmm.
I might
Yeah.
also say that as 10 times 1.5,
Hmm.
like 1.5 tens is 15.
Hmm.
So since you scaled the workers by 3 halves, then you're going to scale the hours by its reciprocal. Then you need 2/3 the amount of hours. So from 12, 2/3 of 12 is going to be 8
Yeah. It's a little
hours.
trickier because when I
It's a
did,
lot trickier.
yeah.
Yeah.
Well, because I saw the 10, and I think because I know there's 2 5s in 10 and 3 5s in 15, right? So like,
Mm-hmm.
so I know there's a 2/3 or 3 halves, but
Mm-hmm.
because it's also not the same relationship on each side, like going from the
It's an
workers,
inverse. It's an
yeah,
inverse
then
relationship.
it
Mm-hmm.
gets a little bit twistier to hang on to.
Or maybe a lot twistier.
Hmm.
Which then begs the question, if I were to do a problem string like this, ideally I would have done direct variation problem strings with non-unit rates, where we would have had the same kind of thing happening. In fact, you're
Hmm.
making me wish we would have done an episode before this,
No.
where we might have done something like, if I've got 5 slices of pizza for $6.
Hmm.
Let me actually change those. This is Pam making it up on the fly. If I had 4 slices of pizza for $5, but then I wanted to have 10 slices of pizza, so 4 slices of pizza for $5, and I wanted 10 slices of pizza, is that also that 2/3 or 3 halves relationship?
I don't know. I
Four,
didn't write it down. You said 4 slices for $5.
$5, and I want to go from 4 slices to 10.
Okay.
Is 4 to 10 also that 1.5? No, that's two and a
Too
half.
fast. Yeah. What?
So that's a 2.5
Uh-huh.
relationship, right?
Uh-huh.
So then you would want to scale the 5 also times 2.5.
Yeah. Yeah.
And so we kind of want to do some scaling like that.
With
Another example would
non-unit.
be, if I'm trying to get from 5 to 6 multiplicatively, I can multiply that by 6/5. Then I could multiply whatever the other side of the ratio table is also by 6/5. That's I don't know that we've done a whole lot of that. Maybe we do that sometime on the podcast, but this
Well,
idea of that there's a multiplicative way to get from any factor, any number to another number, and it has everything to do with fractions. Go ahead.
well, I appreciate you taking me down the road of doing both at the same time. inverse and scaling
There you
by.
go. Yeah. So we're not only scaling by this nice 3 halves, but we're also having that inverse relationship. You're welcome, Kim. You're welcome. Because you are up to it. And we are having so much fun. You love being on the podcast with me.
I do. All
Hey,
right.
can I tell you what a lot of kids do at this point?
Sure.
So some kids will do what you did with the 5 workers and 24 hours to say that 5 to 15 is times 3. That's 3 times the amount of hours. And so you need a third the number of workers. 24 divided by 3 is 8. Many kids will do that. Other students will say, hey, I'm noticing that we've already got 10 workers on the chart they took 12 hours, and we've got 5 workers on the chart. They took 24 hours, and then they add the 10 workers plus the 5 workers to get the 15 workers. And if you do that 10 plus the 5 is 15, then 12 plus 24, they get 36. And then we get to stand back and say, you're saying that if we have, say, 3 times the number of workers, it's going to take them more hours? Like, does that make sense? And this is actually, like, we are doing this really kind of fast, this idea that if you double the workers, it takes half the time. But that often is, that often takes some working with students where they actually have to maybe do a thing. Like, I actually had students at one point, I was like, if we were going to erase this board and it took 3 of us a minute to erase the board. Okay, now you 2 go sit down. There's only 1 of us now. How long is it going to take me to erase the board? Less time or more time? And they were like, oh, more time. Like, we almost had to have the act out the kind of thing to get this inverse relationship a little bit more secure.
Yeah.
Another thing that students will do sometimes.
I know.
Oh, yeah, go.
Well, I was going to ask you, but I wanted us to be a little more streamlined with the problem string, but we've already derailed a little bit. But do you have kids? do you have kids that say, well, it's in between 15 and 20?
Yeah,
so
absolutely.
It's going to be in 15. Yeah.
Yeah. And that's
a trip.
We have 20 workers and 10 workers, and their corresponding time is 6 and 12 hours. So if 15 is in between 20 and 10, then they'll say, what's in between 6 and 12? And that's 9. Now we're really close. Now 8 is the correct hours, but they get 9 hours, and that can definitely be tricky. Tricky to have them think about. Yeah. Nice. Yeah. Hey, one more question. Yeah. I wonder, Kim, you wake up one day and only 1 worker shows up. You got to clear the field. How long is it going to take that 1 worker? If it takes 20 workers 6 hours to clear the orchard, how long is it going to take 1 worker to clear the orchard?
That's unfortunate.
Yeah. Sad day for that guy.
That's going to take 120 hours.
Now that seems really random. Where did that 120 come up?
How did I went back to the 10 and I said, we have
10 workers?
Okay. I went to the 10 workers. Okay. And I said, we have a tenth of as many workers. So divide by 10 or times.
Nice.
1/10. And then I'm going to need them to have 10 times as much time to do it.
And so 12 times 10. Sorry, I didn't mean to interrupt.
That's okay. 12 times 10 is 120.
Okay, that's a great way to do that. I wonder if we were to go from, say, like the 20 workers took 6 hours, the original, if we divide the 20 workers by 20 to get 1 worker, then it's going to take 20 times the amount of time, and 6 times 20 is also 120. Cool. At that point, well, actually, maybe I'll do one. Will I do 1 more? What if we only had 1 hour? How many workers would we need?
1 hour? We need 120 workers.
How do you know?
Because the one guy took 120 hours, but if he brings a whole bunch of friends, they can all get it done in an hour. There's 120 hours worth of work to be done.
That's really interesting. You're saying that if it takes 20 workers 6 hours to clear the orchard, there's 120. How'd you say that? 120 what?
120 hours worth of work to be done.
Yeah, and sometimes we call those worker hours. So in this scenario, it's sort of 120 worker hours of stuff, right? There's we need to get that done, and we can make it happen where we have 20 workers and it takes 6. And so I might at that point actually look at the table, and I wish we were visual here, but I've got 20 workers 6 hours. 20 times 6 is at 120. The next entry we have is 10 workers took 12 hours. 12 times 10 is 120. And the next entry was 40 workers, 3 hours. That's 120 worker hours. The next one's 5 workers, 24 hours. That's 120 worker hours. So every one of these is sort of ending on this 120 worker hours. So as I kind of look down the table and we start to note, sure enough, every one of these workers numbers times every one of these number of hours is 120. I might below that table then write, it sure looks like the number of workers, X, times, and I'm going to write multiplication, the number of hours, Y, is always equal to 120 in this particular scenario, because we started with the 20 workers taking 6 hours.
Mm-hmm.
So if that's true, we now have an equation, X times Y equals 120.
Mm-hmm.
That's kind of nice.
Mm-hmm.
And so if we wanted to solve for one of them, we wanted to say, hey, what if I wanted to know how many hours it's going to take me? Well, then that's sort of, if Y was the number of hours, then Y is equal to that 120 worker hours divided by the number of workers, divided by X.
Mm-hmm.
Now we have a function where Y equals 120 divided by X, and we could graph that, and we could look at what happens. The more workers you have, the less time it's going to take. The fewer workers you have, the more time it's going to take. And we get a very nice curve that comes out. Showing that non-constant rate of change in that inverse relationship. Kind of cool.
Yeah, it's cool.
Yeah, nice. So when we've done other ratio table work on the podcast, we did direct variation. Sometimes we call it the situation is directly proportional. Today we were talking about inverse variation, or we can say that the situation varies inversely, or it's inversely proportional. So that was kind of fun. Let's maybe do some more of that sometime.
Yeah, sounds great.
Woo! All right, y'all. Thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable.